Welcome everyone to study analysis or calculus with me. Um, so I decided to make online notes. I initially started with handwritten notes, so I'll be using both because the first part, or when I was doing my handwritten notes, I just quickly went over it. So yeah, let's get into it. First of all, this is analysis 1 and 2, which I took at ETH. And for analysis 1, we look at the foundations, sequences, series, functions, sequences of functions, derivatives, ODEs, differential calculus in multidimensional space. We'll look at extremas, integrations. I'm actually not sure when it switched to analysis 2, but yeah, we'll look more for integrations, potential fields, vector analysis. I think this one is also in multi-dimension, yeah. Topologies, yeah, and then we have some other add-ons. So yeah, let's get into it. For me, it's already 9, so I think I'll maybe do an hour and sleep. But yeah, it's been a rough time. But somehow I wanted to do it earlier, but yeah, not feeling too great. So happy for anyone who's listening to me. So yeah. So yeah, chapter 1, foundations. What do we do here? So yeah, let's just look at it. Quantifiers, so how to read math. This means for all x, there is one x, or there exists at least one x, and there exists exactly one x, there doesn't exist an x. A and B, A or B, not A. If A, then B. Yeah, these are just notations. X belongs in A or is in A. A lies in B. Yeah. Yeah, A union B. So combined together, or the intersection. And we have the empty set. Negation rules, quite easy. If we have it, we just invert everything. So we would invert A, flip the end on or, and yeah, negate De Morgan. Also had it in Digitech. I guess these are a bit more special, yeah. So yeah, if it's all, then there is one. So yeah, so what does this do? So if we need to prove something, we can like rewrite it and prove the other thing. So yeah. Yeah. Maybe this won't be the best of my series. It's like a 1 week post breakup, and I'm trying to do stuff, but it's going. So yeah. Actually, why do I have convergence here? This should be somewhere else. Whatever. I'll maybe fix it at some point. Yeah, so proof examples, yeah, assume A, derive B, then we can, instead of proving A to get B, we can prove that not A is not A, not B is not A. I think the initial topics are not too interesting, especially if you have already seen it, but still good to go through. So we have different maps, Abbildungen. If it's surjective, then every target Y is hit at least once. So the map covers all of B, all the b values are there exist in a. That's that. I think I have graphs here. Well, only for the other ones, but you can imagine like the whole region is getting. The image is the whole region. Injectivity. Different inputs never give the same output. So you can undo on the image. So this means if they have the same value, then the x must be equals. No. And here we can see this would not be the case because we have one y value. For example, 2 has like an x here and an x here. So this would not be not injective. And then if it's surjective and injectivity, then we have bijectivity. I only know the German word. And if we have that, we can also get the inverse. That means all the region A maps to all the region of B. So any value of B can be calculated back to A. Yeah, and how do we see that? No, I guess we don't have anything here. But you can imagine just a straight diagonal or like a diagonal line, and then every x has a y value. Composition rules. Yeah, so if two functions are injective, then G. What was this called again? I'm too tired to think tonight, but yeah, it's also injective. So basically, it's like if both of the functions are already something, the rest is, or the combination of the two, the chain of the two, is also that. Yeah. Supremum and infimum. So basically, it's a value that is greater than all the values in the set. We have that somewhere. Yeah, and infimum is the smallest value in or just barely in the set. I mean, at the edge. Yeah, and infimum can be the, so we can convert them with minus. So we have this thing here, like here the the maximum supremum would be this value 1. Yeah, and here it's like not included, so it's 0 and 1 are not included on this line, but 1 is the supremum and 0 the infimum. I'm not sure if I'm talking to what is it called? Not too loud. Yeah, here's another visual effect, I guess. What is this? X cubed for them to be smaller than 2. X squared. So yeah, so like square root of 2 does not belong to A because it's not a, what is it called, quotient or whatever. Yeah. Well, rational numbers. Oh my gosh, how do I not even know that? But yeah, so all the square root of 2 is not the rational number, but it's the infimum and supremum. Triangular inequality, I guess you have seen it quite a bit. So you have the absolute value of x plus y is smaller or equals to the absolute value of x plus y. For vectors as well. And yeah, if it's minus, then see the other way. So when do we use it? Estimate integrals, limits, norms, blah blah blah. What's this? Yeah. And then let's get to sums and products. So we have telescoping sums. Why do I feel like it belongs to somewhere else? Whatever. So yeah, if it's starts at m to n, and then this one is always minus the one before, so in the end it's just the last value, like here, the largest value and then the first value, because this gets cancelled out when we expand it. Does it show here? No. And then for product telescoping, similar, because if we times again, we just can like cancel out. Well, I guess this is another useful formula. Yeah, what is it called? The sum of increasing numbers is this. And yeah, we have different sums that, yeah, maybe you can look at if you ever need it. Good to see it and then know, well, approximately how to do it. Maybe I should have like added like the steps to prove it, but whatever. Yeah. So yeah, here you can see like, well, how we could use the rule. I'm sorry that I'm low energy today, but yeah, maybe I'll be better tomorrow when I want to continue going through these things. So yeah, so I guess here we see that this approaches 1. Why is this even in here? It shouldn't be. Whatever. Somehow got messed up. Induction is to prove something. So we first prove a base statement. So we check a first case and then we prove that it works for n, and then that it also holds for n plus 1. Or like, I mean, this is the one thing, right? It works for one case, and then we show that it works if n holds. So let's just assume this is true, and then n plus 1 also is true, then yeah, everything after the base case, we would have proof that it's true. Yeah, and usually you have to, let's go through an example. So yeah, base, easy to prove, and then both sides we would have to do, like, we assume we know like n is true, but then we do n plus 1, and then we try to like mush it together that it turns, that we can like, yeah, write it in the form. So yeah, if we see this, we go to n plus 1. This is what we get for only until n. And then if we sum one more k, which is n plus 1, basically we just add this. And then we can manipulate it a bit, and then we get this, which would be for n plus 1 and n plus 2. And then we prove that partial fraction decomposition. This is useful for integrals. So yeah, the workflow is, oh, I don't even know, what is this, denominator, nominator, or something. Denominator is the bottom one. I guess nominator is the one on top. A numerator, yeah. So if the degree of numerator is larger than the denominator, then we do a polynomial division. I hope, well, probably not, but hopefully you guys know what it is. I'm not gonna go through it. Do I have it here? Probably. Yeah, here I had like a lot more stuff. Or not, or yes, I do. So yeah, let's see if the top has a higher. Well, yeah. I didn't perform division here, right? I don't think so. I don't know what I did here anymore. I just expanded. And then, oh, I guess I divided it once, maybe. And then, but I didn't put the steps here. Yeah, and then we get a polynomial. And then one quotient where the degree in the numerator is smaller than the denominator. And then we want to factor q and then find all the zeros for it. Let's see a case. Yeah, so if we have this, we factor the denominator. So this we can write as x plus 1, x minus 1. And then we know if we take them out, it's like a plus b times this. And if we mush them together, then we would have to do a times this value plus b times this value, that they have the same denominator. And then we can solve an equation where a times this plus b times this must equal 1. And then we see a must be minus b, so that the x cancels out. And then to add it together should be 1, so yeah, minus half and minus half. Yeah, because 1 is minus 1 and plus 1. So yeah, we get like this. What is here? What? Oh yeah, 1/2. Oh, wrote it like that. So yeah. Guess here's what is this method map? If we need to disprove for all, we found one counterexample. If we need to prove injectivity, then we show that if it's the same value, then it must be the same x. Well, yeah, you get it. You can read through it. Exercise, I mean, I put some, but I never looked at it. Should I do? Well, negate. I mean, maybe I'll do it on my own. You guys can like go through it on your own. Probably will be too much of a waste of time for now. And then chapter 2, sequences. So what are sequences? So it's a sequence of numbers. So yeah, convergence, bounds, Cauchy sequences. Okay, yeah. A sequence is an order list, so we have different numbers, a1, a2 till an. And analysis asks whether the list settles near number, so it converges towards a number, or so it's bounded, or if, you know, it goes to infinity or somewhere. Theorems. Monotone. I'll have to close my window soon. It's like storming now. Monotone bounded sequences. A sequence that only moves upwards but stays below a ceiling must approach that ceiling, so the supremum that we saw. And yeah, and falling sequences approach an infimum. So you can imagine like it just falls. I think this would be one of the charts up here. So if it goes up, then at some, well, it's telescoping sums, but it will be the same thing. It will like, right, it approaches a bound, so it goes up till it towards the supremum. Yeah. Yeah. Cauchy sequences. So for all epsilon, there exists an n such that there exists an n which belongs to natural numbers, and for all n where m is larger than n, an minus am smaller than epsilon. So what does this mean? So we have an n here, and we have an m which is larger than the n, and all of that, those will have a smaller error. So let's say, I think it's here, it's like we choose this one as our n, and then we have an m. These are all smaller margins than this. Right here we can like change the margin. We can like choose any margin, and we would see, we would have like this point, and then everything else is like gonna be towards it. So that's like monotone, I guess, Cauchy. Cauchy sequence. Yeah, it should have been here, the plots. Somehow it messed up. So yeah, an converges, an is Cauchy, it's the same thing. In contracting sequences, so we have a C which is between 0 and 1, where an plus 2 minus an plus 1 is smaller than C times an plus 1, an minus 1. So that means the difference gets smaller by a factor of C every single step. I'm not sure if this is something like Leibniz. Rain, 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 it does good. And then Bolzano-Weierstrass. So if we have a bounded sequence and it has at least one accumulation point where it converges to the limits. So if we look at the chart, we can see like these points in the end, they all converge to this one value, right? They're all like one. Yeah. Oh, we have quite a bit more. divergence to infinity. Oh wow, it's raining quite hard. Let me stop. Oh, I didn't want to stop it. I just wanted to pause it. So yeah, some important limits. If we have a negative s, it will converge to 0 because it's 1 over a super large number. What do we have here? If it's smaller than 1 and to the power of n, then we also know it converges to 0 because it's small numbers multiplying each other. If n is to infinity, then it just converges to 1 if it's larger than 0. If not, it's not gonna be, I don't know, like I or something. And yeah, if this 1 over n, so it's the same as this one, theoretically. And the square root, I guess, converges faster, so it converges to 1. I think I had like what converges faster than what, but I guess not here. Yeah, here we see that, yeah, to the power of n converges faster, so decrease faster makes this go to 0. Go towards the log, natural log goes towards 0, it goes to negative infinity. Yeah, some other things to look at. And then yeah, in these we can actually use L'Hopital rule. So if they are differentiable and it's like 0 divided by 0 or infinity times infinity or things like this, then we can, instead of when we take the limits of this, we can take the limit of the derivatives. And usually that's a lot easier. Yeah, let's look at this example. It goes towards 0. So x times ln x, we can rewrite that to this factor. So yeah, this would be infinity times infinity, but yeah, we can do the derivative, and then here we would see, oh, this goes to 0 faster, right? So, or I mean, yeah, this cancels out, 1 is left, and it goes up, so it's like minus x, and that goes to 0. So basically meaning this goes to infinity faster. Special tricks, what do we have? We have sandwiches. If an is bounded by 2 other sequences with the same limit, then we know what the limit of an is. If the other 2 are easier to calculate. What was this? Yeah. So let's continue. Yeah, I think I'll just do until chapter 2, and then tomorrow I'll do the rest. Yeah. Well, I guess this was it, right? We could do some questions here. Goes to infinity. This one is larger, right? It's like 3. And we see it converges to 3. So if these cancel out, because this is too small, we can ignore. And here the limit to infinity, this is always between 0 and 1. This gets large, so it goes to 0. Sandwich theorem, yeah, I guess. show that an equals 1 plus 1 over n to the power of n is increasing and bounded above by 3. Well, yeah. I'm too tired to think, and there are no solutions. That's fine. So for this, yeah, we can do L'Hopital. So we take the derivatives e to the power of x, and then this gets to x and disappears, turns to a constant. Oh, and then e to the power of 0 is 1. Oh, and because 2x, right, 2 comes out, and so, yeah, 1 over half. Prove that this. So yeah, if this turns to a large number, we would not care about. Oh wait. When? Well, I'm a bit tired. But yeah, I think I'll see you guys tomorrow. I'll shower and sleep and hopefully not be too sad. So welcome back to my analysis calculus. So let's continue with chapter 3. And I think I'll take it slower. Oops, that was the wrong one. Where was it? Here. Yeah, let me open up Notability as well. But yeah, I think today I'll go through slowly, so for myself to learn. So yeah, it's interesting to see you guys. I guess it's nice if anyone is studying with me. So yeah, let's look at the next topic. Series. First we have sequences, it's just numbers, and now it's series are just a sequence of numbers, and that series converges to something. A series, so sum of numbers, it's the limit of partial sums. Yeah. Okay, so let's see. Absolute convergence. So if the absolute value converges, then the series converges as well. Yeah, that means we add if it's minus, it's a positive number. Yeah, and this could have positive and negative, so it can make it smaller, right? But if even this converges, then this also must converge. Yeah. So yeah, 1 over n converges because we know 1 over n just diverges. So if we change signs, it should converge. Yeah, this similar. Okay, today I should be in a better mood. So Leibniz criteria, if an is monotone decreasing, with an going to 0, then if the sign changes, it converges. So yeah. So it has to decrease. Let's see this 1 over ln. We know that this one decreases. Sign changes, so it converges. Yeah, we know if sign doesn't change, it diverges. Because, yeah, compared to the harmonic, so 1 over n, it's this one goes small, ln grows slower than n. Ratio test is if the next value smaller than 1, smaller than c, then it converges absolutely. Then if the limits exist, so we can say when it converges or diverges. So when do we use it? When we have factorials, so we have to, we can compare ratios. Let's go through an example. We have this, then we have n plus 1 right on top and 3 on the bottom, and then we can see for a large thing, it's over 1, then it diverges. And yeah. What is this? Dirichlet. We cover everything here. Here he is. I mean, this one, if it doesn't go to 0, then it diverges. That's clear. Yeah, and these two is if we know a series then converges or diverges, and if it's larger than the one that converges, then it also converges. Diverges the other way around. Yeah, then we have important sums. Okay, good. When do we use this? So if we have sine over n, this oscillations with decay. Now let's look at the root test. So if let q equals this, the limit of the supremum of n to infinity, and then we have q is smaller than 1, then it converges. Larger than 1, that diverges. Let's look at example. So we have something, so that's something in the power of n, right? So we can take the roots, this, to the nth power, so we just see the inside. Yeah, and then we can say it's smaller than 1, then it converges. I mean, it makes sense, right? If we have a number that's smaller than 1 to the power of n, then it converges. Cauchy product rule. Does this, if the sum of those both converge, A and B, then Cn converges absolutely to A times B. Yeah, I guess makes sense. Convergence criteria, decision tree. Yeah, first check that it goes to 0, and then we look at the shape. So yeah, P series, it's the power of n. We have ratio if we see factorials, or root if we see power to the n. Yeah, and then how to walk through what to do. And this, we saw the homogeneous series. If it's, as soon as it's larger than 1, it converges. Yeah, okay. I think this we already saw. Majoran criterion, yeah, we have something converges which is larger than an, then an converges as well. Yeah, so basically we can check. So remove some numbers. Same for the other side. Integral test. So if it's positive, continuous monotone, decreasing, then we have fn and x. Let's look at an example. We have to the power of minus k. Check the integral, and we see that we'll take -1, and we put in 1 to the power of something, it's still 1. Okay, minus 1 comes out, yeah, so. So we know that's smaller than infinity, so if the integral is bounded, then the sum should also be bounded. Makes sense, because the integral takes like every value and sums only like at the integers. What is this again? Limit comparison if a and b are greater than 0 and the limit of the ratio equals to a number, then a and b converge or diverge together. So they're just apart, a same factor. What will be here? En equals this, and if we divide by n squared, so it's 3 n squared, so it's like a factor of 3 compared to 1 over n squared. And this one converges, so we know this one also converges. Well, it's an easy check. Some formulas to get the sums. I think this we already saw a few. So a number to the power of n, can rewrite it as like this. The sum going up to n, we saw this formula again. It's k squared. It looks like that, or like that, but I don't know it by heart. Yeah, this the same or similar. No. Yeah, and then some things to look through. I'm not gonna memorize everything. I think I'll take a nap. I'm still not feeling too awake, even though it's only been 15 minutes. Let's continue. I'm back. Wait, let me pause it. I have to check something. Okay, let's continue studying. Let's look at some, where did we end? Some common infinite series. So Taylor's. So e to the power x, we can expand it to this. These two are the same. X times e to the power of x, just be this plus 1, right? And then, yeah, and then we take the derivative, we get, or I guess it's a bit more complex. But yeah, this would be the series, or I just list them out here, the sine, cosine. It's like, maybe it would be nice to also like write it out to see what it is. It's also like an alternating series, so one time it's minus 1, one time it's plus 1. Yeah. ln 1 plus x, 1 plus a to the power of a. Yeah. Coley. Some Euler link. It's also nice to know e to the power of ix is cosine x plus I imaginary sine x. Sometimes this is used. Recognize a series. So add 2k minus 1, right, to the power of n. So you know sine of 1. Oh gosh. But yeah, I'm not sure if I will still be able to do these exercises because yeah, you really need to know all of this. So either I have a list of all this, and then when you see this, you try to like form it into something that has this form, and then and then you can compare. Let's go to power series. This is a power series centered at x0. Can get a calculate a convergence radius, and yeah, that's when Cn, so R is 1 over this. So it's basically to know how far away we can go. At the boundary, we need to check separately. Anything else, it goes to 0. Let's see an example. X to the power of n over n squared. If we take plus 1 over the last one, get this. Doesn't make sense. Cn n plus 1. Yeah. And then if we calculate the limit, we see this goes towards 1, so the convergence radius is 1. What do we see here? Partial sums. It converges k squared. The harmonic diverges, but I think it's hard to tell, but it always, it's gonna infinitely get larger, but like very slowly. Method maps, what do we do? If an doesn't go to 0, it diverges. If it's geometric, we do a p-series match. Factorials, we check the ratios. The power of n, we do the root test. If the series is alternating, we can use the Leibniz rule. It's positive, and if n is decreasing, we can either try integral rule or compare with a different series. Yeah. Converges. Do a ratio test. What would that be? N plus 1 is left over divided by, no, above is n plus 1. So n plus 1 over 3, I think. Yeah, anyways, it diverges. This is larger, grows faster than this. Alternating, then we see, oh, Leibniz, right? This is something that goes towards 0, it alternates, so it converges. Find closest form and limits, we could just check k squared with a limit. Well, it converges, right? What is this, A4? Oh, okay, so I guess we write it like that. Radius of this, the ratio goes towards 0, so we know the radius is infinite. I need to do the questions parts differently. Well, maybe for a different subject. I'll anyways take again this calculus, but then for quant finance, hopefully, and there, yeah, do some more. Functions. So what will we look at? Continuity, compactness, analyticals for limits of functions, and yeah, theorems and proofs. Or no proofs, just theorems. So function is continuous if a small input changes produces a small output change, and on closed bounded intervals, continuous functions attain a maximum and a minimum and take all intermediate values. So yeah, we can imagine it's a continuous function, and then it's bounded, then it's bound to have like in between a what is it called, a maximum and minimum value, and between those they need to be connected between the two bounds. Yeah, where to start? Epsilon, delta, or sequential proof, piecewise function at breakpoint, root existence, max min. So we'll look at this. So let's go to the theorems first. A continuous function stays inside an epsilon tube around f x0 by keeping x close to x0. What does that mean? Let's look at this. Or actually, this is what explains this. So we should have first look at this. On the real values, it's continuous at x0 if there exists an epsilon larger than 0 and a delta larger than 0, and for every x in D, so x minus x0 is smaller than delta. So if we have the, let's call the x values, if they're smaller than this, then we can, then the output, the y's of the function is smaller than epsilon. So let's say we have a fixed epsilon, and then we can find one delta. Let's see if we have something like that. Well, not really, but let's go for something else like above. Where was it? I thought, oh yeah. So let's say this is our epsilon here. So we can set a epsilon. Let's say we put this one. Well, this is not in the function middle, but let's say like this would be down here, or this point will be up here. Then we can say we can find, or if it's like really small, we can find a value, so an x, where it will be between this. So we can say, oh, the point, well, it's already really close. Well, it's not the best example. Hopefully get what I mean. Probably not if you've heard it for the first time. So yeah, it's anyways like more like a recap. I'm also using this as a recap for myself. Sequential characterization. If f is continuous at x0 for every sequence, xn goes to x0. In D we have, wait, if f is continuous, and then for every sequence, so I guess it's a function sequence, yeah, it also goes towards it, or not a sequence, or the x values as they near x0 nears 0, yeah. Okay. For every sequence. Also, it's basically we just look at a subset, but we can look at every subset, and it has to be true for that. Okay, continuous image of an interval. If f is continuous on an interval I, then fi is an interval, no gaps in the range. So you have our input, it's continuous. So from x, for example, we go slowly from 0 to 1, then the output at y should also be continuous. Lipschitz and uniform continuity. So if f of x minus f of y is smaller than a number times x minus y, then it's Lipschitz. So yeah, that would mean that that it never grows, the function never grows above a certain value, so its derivative is never larger than this L. Uniform continuity. So for all epsilons, there exists a delta, and for all xy in D, x minus y is smaller than delta. So we find such a delta where f of x, well, it's, yeah, smaller than epsilon. So anything that's smaller than delta is smaller than that epsilon would make sense, I guess. Yeah, when it's uniform. And the most, so yeah, first we have continuity and then uniform continuity. If it's like this, then it's Lipschitz. It's bounded by that. We see the strength of these continuity. Yeah, and this is what I said, if it's Lipschitz, so if the derivative has a maximum value, it's bounded by that. We know G is continuous, and it's always larger than F, then F is also continuous. Intermediate value theorem. If A and B is continuous, then yeah, we have a C, and then we can find xc. So if we find a value between the two bounds of the output, then we can find a value between the x inputs, x and y, a and b, where it will give us this intermediate value. So let's say if we start here, we end here, then we can find any value like between the height of 2 and 0. Let's say, for example, here we would have for sure an x value that would give us that. Let's look at, what is this? When to use it, existence of roots. So we know it starts here, ends here, it's continuous, and it must cross the 0 line. Fixed points, intermediate value theorems without solving explicitly. So let's say cube has a root. X to the power of 3 minus 3x plus 1. And then we can check that one time it's lower than 0, one time it's larger, then it's continuous. We're sure that there exists a root in between. Yeah. And just to show you, extreme value theorem. If f is continuous on a compact AB, then it attains a minimum and maximum. Already said that. Monotonicity and inverse. If it is strictly monotone, continuous, then the interval is injective, right? So it has an inverse on that, and continuous. Well, on that domain, it would be bijective, right? But or not bijective because it doesn't map all the image plane. Mean value theorem. So yeah, the derivative equals this. Preview. Oh, I guess we'll look at it for derivatives. But yeah, we can use that. It's this. Local extrema via second derivative. It's just determining if it's a local minimum or maximum. I think this is easy. Probably look at it more. Formal divergence. If x goes to infinity, when x goes to infinity, and if for all m there exists an r, where x is greater than r, if x must be greater than m. So you have it goes to infinity, then it just means, yeah, we can find a value where the function output would be larger than that value. Checking continuity. Elementary functions are continuous on their domains, and then sums, products, quotients are defined, compositions preserve continuity. Piecewise, at the breakpoint, the two values closing in on each other needs to be the same. Let's look at this example. Piecewise, x squared is continuous, and if we have that x is smaller than 1, so it goes up until 1. And then if it's larger than 1, we have 2x minus 1. Well, 2 times 1 is 2 minus 1 is equals 1. So the left and right side is 1, so it is continuous. What would this be? F of x is the absolute value of x divided by x. For x not equals 0. So let's see. So if we go from the positive side, it's positive divided a positive number, it will give us 1. If it's negative, then positive divided by negative, that will give us -1, so it's not continuous at 0. It's like a -1 and it suddenly jumps to 1. Continuity in multi-dimensions. If that is continuous at x0, if for all epsilons there exists a delta where x minus x0 is smaller than delta, well, it's the same. We're the distance. Yeah, here we just use, yeah. Oh, yeah, I've not been sleeping too well this past week, but it will get better. Even though I went to sleep early and wake up early, but yeah, it is how it is. Polar trick, yeah, we can convert it to polar coordinates, and when we let r go to 0, then the limit should only depend on phi. Makes sense. The limit must be independent of phi. Sorry, so yeah. So the limit doesn't matter so we have a point here, and then if we're outside, if we go towards it, the value should only depend on r and nothing else. If two paths give different limits, the multivariate limit does not exist. So if we find, we go here, it's different than there, then it makes sense that it's not continuous. So if you take polar coordinates, x times y, and then this is r. So r squared cosine times sine, and then what would this be? Well, I should make it write out the steps. Let's head to chapter 5. Actually, I'll start to move faster because it's all boring stuff, more or less. Sequences of functions, pointwise and uniform convergence. So now we look at functions that have a sequence. So if fn to f goes towards f is pointwise, if each fixed x is hit eventually, uniform convergence adds 1 speed and epsilon for all x at once. And that's what makes the theorem safe. Yeah. Convergence methods. Pointwise convergence. So the function fn converges pointwise to f if for any x values there's an n that converges towards it. Yeah. Uniform convergence means exists an epsilon, so we define when that happens. There exists one natural number, and for all n's that are larger than that n, so for all the functions that are larger than that, And for all x, the function needs to be smaller than epsilon. So equivalently, this equals the supremum goes towards 0. So difference from pointwise and does not depend on x. So it's for all of the x. And here we can choose n for the x values. Classic counterexample, x to the power of n and 0 and 1. It's pointwise limit, right, of f of 0, f x 0, oh yeah, so for any of the n is super large and it's 0, but then f1 it's 1, so it's not uniform. What is this? Pointwise to step function. So here we see uniform limit of continuous functions. If fn is continuous and it goes to f uniformly on D, then f is continuous. Cauchy criterion for function sequences. Fn is uniformly Cauchy, or D. For all epsilons. Man, the memories sometimes just pop up. I was just like thinking about other stuff. And that made me sad for a tiny second. But yeah, let's continue. It's uniformly Cauchy if there exists an epsilon and there's an n for all m and n larger than that number, they are smaller than epsilon. Yeah, and if it's the whole domain, then these two mean the same thing. Normal convergence converges normally if distance of that smaller than infinity. What does it mean? Yeah, this is the strongest one. This is not a function. Why is it here? Or not, I guess. Okay, how do we prove uniform convergence? So given f and omega, we want to test if it's uniform convergent. So we check the pointwise limits. So yeah, if it equals, we estimate if it goes to 0, then the convergence is uniform. I should have an example, right? It's x divided by n. So as n goes to infinity, this should go to 0. Fn minus at, what is it called? The large number. And yeah, I'm not sure. Yeah. Like this, I could like ask. I guess you can look how I study, right? I should just study. Wait, where am I? I'm on localhost. Perfect. All I can do is just 5.2 examples. My mind is not the brightest today. Like I cannot focus for some reason. Why is it like this? I should be working hard. Should focus on my things that I want to do. Focus on my life. Yeah, it's a bit slow. So yeah, actually here we see like x to the power of n at 1 on this domain at 1. It goes to 1, but it's 0 between 0 and 1. Then supremum equals 1. Let's see. Oh my gosh, I'm tired. So yeah, this is better. So we show it's uniformly. First, pointwise, we fix x 0 and 1. Then x divided by n goes towards 0. So f of x equals 0 for all x 0 and 1. What do we have here? Fn minus fx estimated. Actually, I don't know one. Yeah, what is it? pick a fixed x and let n go to infinity and see if n approaches that limit is fx. Yeah, so goes to infinity, so f of x equals 0 is our function. Do we ever say that? Oh yeah, I guess here, yeah, we see our function is 0. We estimated just any x would be the absolute value, right, divided by n. This would be a function that's smaller than 1 over n because it's between 0 and 1. So yeah. That's not uniform. Oh, here it doesn't include 1 because it's still like, even if we have a super large, it still goes up, like starts going up very fast at some point. Or actually, let's walk through it. The limit function will be 0 in this interval and 1 at there. Limit is discontinuous. Oh, we have a new example. Show that this functions as uniform on 0 and 1. So at x equals 0, 0 divided by 1 is 0. N of 0 is 0. For fixed x larger than 0, you have x divided by 1 plus nx. And then if we let that go to infinity, can we do divided by x, right? And this goes towards 0. So it's 0 on, so the limit is 0 on that whole space. And then we start estimating an en for an x larger than 0. X over 1 minus nx is smaller or equal to 1 over n. So we can use this here. Because yeah, it's like this one, right? Yeah, we have a positive number here. Make it smaller. X equals 0, the term 0 does this one is smaller than this, and this is only dependent on n. So we can say it confirms uniformly. Here, swapping limits with derivative or integrals. have the limits. So if it is uniformly, we can swap the integrals. Take the limit out if fn is continuous, pointwise, and uniform. This up here is bounded by 0 and 1, so it's smaller, equal to this. Yeah. Okay, let's get to derivatives, something more fun. Rules, mean value theorem, convexity, Taylor polynomials, and Newton's method. So the derivative is the best linear approximation of function near a point, and the mean value theorem turns average slope to an instantaneous slope somewhere inside. So we can use that for Taylor. Taylor refines that to a higher order. So the basics. So let's start with this. The derivative of this function is if f(x plus h minus f of x) divided by h, and the limit goes to 0. So this is the slope of the best linear approximation. H of x is that plus, yeah. And if it is differentiable, then it also means it's continuous at the point. And this is a linear approximation, this is like Taylor series expansion, we'll see. We can use the first derivative always. Some rules, if we have sums, f plus x derivative, it's just separately. If it's product, we have a product rule, so it's the first one derived times the second non-derived and the other way around. Quotient rule, this can be remembered. If not, then you can like turn it to a product rule, and then you should get the same. Chain rule of f and then g. So f is inside function of g. And we have f primed of g times g primed. We see that a lot for substitutions. The inverse of a function is 1 over f prime times the inverse. If f is injective. When will we have I used that? I mean, for exam questions, I think I've seen something like that before, where it was easier that way. This one I think you should know, general product rule. Okay. Example, integral rule. Like this to power of t. It's x squared. Right, minus. Take the derivative. So it should be the same as f of the lower bound. What would that be? E to the power of 0 is 1. And the derivative of that is 0. The minus. It should have been, sorry, the other way. X squared comes first. So f of x squared, so e to the power of t, we just replace it with s squared, and then times the derivative gives us this. And because of 0, it's 0, the derivative, so we don't have the back term. So it's like an easier way to integrate and derive, I guess. I feel like I've never seen an exercise like this where we first integrate and then we derive to the bounds, but I guess it can happen. Some common derivatives, x to the power of something, stat minus 1, and that value comes forward. Yeah, for natural numbers, for exponentials, e, yeah, this should be clear. If it's a to the power of x, then we just have ln a. We can just like do e to the power of ln a x to get this. That's why the ln a comes forwards, like this rule. Ln of x, the derivative is 1 over x. The sine is cosine, cosine is minus sine. The tangent, we can derive it from, what is it, the sine divided by cosine, taking that derivative with the product or quotient rule. Yeah, arcsine, good to know. Cosine, you see this kind of stuff. You see 1 over square root of 1 minus x squared. Arctangent, 1 over 1 plus x squared. Oh man. Yeah. There's this example, x to the power of x equals ln of x e to the power of x, right? These two are the same. Chain rule. So the derivative of this would then be it will be e to the power of x ln x, which is x to the power of x times the ln x comes out. Well, why do we have well, I guess because can we Wow. I'm really low on energy today. Maybe it should have been better. No, I should do it. I should not like push it backwards anymore. Let's do this. Mean value theorem. So the idea is somewhere in AB, the tangent is parallel. So if this A, this B, the tangent is parallel to the secant through A, f of A here, and B of B. So we say there is at least somewhere where it's, you know, right, if it goes up first and then goes down, it's somewhere, it needs to be like faster, dropping faster than this. But we can use this to estimate. So we see this is somewhere like around here, right, the medium falling. Because here we have it falls faster and slower than the medium. Yeah, and if it's continuous differentiable, then we can do this. There exists a C somewhere here in between where the derivative equals to this number, this formula. So that's why if we like reduce A and B, we would get like closer and closer to the derivative at that point. Or at the point that we want, let's say here, right? But whatever. Yeah, if the derivative is constant, equals 0, so it means it doesn't grow or fall, then it means it needs to be constant. If it's larger than 0, the f is increasing. Yeah. Why am I feeling this? I need a break. I need to think a bit. I'm back. Let's go faster. Oh man, if anyone can get me into the US, I would like appreciate it. I feel like I'm still not over it too much. Yeah, it makes my brain a bit tired. Somehow I can't focus anymore right now. But I want to finish this today so I can do like other stuff. I still have like that I want to do. Yeah, do some more of the C++ courses. Exciting stuff. Sometimes the path we take is lonely. And you're hearing me rumbling. Convex functions. So graph lies below chords. So that means the second derivative is positive. That means the derivative is increasing. So something like this, convex. So it falls slower. It can fall, but it always falls slower and slower and starts growing and growing. And what is the other way around also exists? Convex and concave. Right. Taylor polynomials. This is quite seen oftenly. If we estimate a function, you can take this formula around a point A, it is f for 0, so f of a is still 0, so it's 1, plus times this. At 0 it's just 1. So what that would mean is, I should write it out, but why is it not here? But so we have like f of a, so the value at that point, plus the derivative of x minus a. So if we go like further out, I could even add an animation where you see that, but I think it's unnecessarily, like I know it. If you guys learned it, you've probably seen it as well. Ground remainder, so yeah, we have, if we only estimate up to n, the remainder can be estimated with this. So this of c, some value in between and x. We don't know what it is, but yeah, so that would be the error. Says integral remainder. Oh, we can also write it in the integral form, I guess. But yeah, not gonna deal with that now. Let's look at an example. E to the power of x, 0. So the remainder would be e to the power, well, it's at 3, right? So 1, 2, 3, 4 times 4, 4 times 6, 24, and then to the power of 4. On this, it's smaller than e, so that's why we can estimate it like this. Newton's method, so if we want to find zeros at a function, we can start somewhere near a simple 0, and then we take this point, x, whatever it is. Let's actually go through this. Here we have 1, we start with 1, take this point, we do minus this function value, so this would be here, minus the derivative of that point, this tangent line, so it cuts at here, crosses the 0 line, and then we take that new position as xn plus 1, and then we start here, and then we see in 2 steps we're pretty close to the 0 point. Here we see at first it's minus 1, 0.25, and then small. Yeah. So let's do a review. Differentiate product quotient. We have the rules, bound. We approximate a function. We can use the Taylor plus reminder. Multiply Taylor series. Cauchy product. Actually, this we should look at, right? Do I have it here more? Cauchy product. What? Did I stop here? Or no? Oh no, it's here. Product of Taylor series. We have G times H. If G is this, H is a series, then it is the sum of this times this equals n. x to the power of n. Cauchy product. We have it here, yeah, product of series. That's x to the power, yeah. Yeah. Let's look at ODEs. Oh, I did like a class on ODEs and PDEs. There it's a lot more. So to me, this is already easy stuff. I already revisited it, but I guess we can do it. So if it's first order and linear, yeah, well, that's just summary. An ODE relates a function to its derivative. Ordinary means there's only one. It only depends on one variable. Linearity and constant coefficients lets you split the homogeneous and particular parts. Yeah. And systems, eigenvalues. Say classify ODEs, and if it's first order, we can see if it's separable or not. Constant coefficients of higher order ODEs can also solve that. And if they're non-homogeneous, we can have to solve that. So yeah, let's see. So the order is the highest derivative. Linearity is if the y's only don't depend on other y's, they're linear. Homogeneous is if the right hand side is 0, but could be non-homogeneous. Wait, let me just have a random thought. Okay, let's get back. So first we classify it. Well, there's many more to classify, but that's not the topic of this course. We solve the homogeneous, we find the particular solution, and then the general solution of these two added together. And then we can apply the initial conditions and yeah. Oh man, it's okay. So if it's first order linear, then we can calculate an integrating factor, which is this p e to the power of negative, the integral of this one, and then we could times this integrator factor with everything, and then well, I guess you could also directly get formula. What is that? Well, I'm not sure if this is entirely correct, but yeah, we would have this integrating factor. Why is this? Oh, yeah. Integrating factor times y, and what? Yeah. Example of the derivative is 2xy. This, I guess, boundary conditions. So you can say y is e to the power of this here, x squared. X integral should be x squared. It's not minus x. I feel like there's something wrong here. Yeah, we have a second order, or it could be higher, but with constant coefficients. So these are just numbers. We can create a characteristic polynomial because we estimate the solution, we guess the solution to be e to the power of lambda x, or rx in this case, and then we have a r squared plus br plus c 0. And then, yeah, we find the roots. If they're real, then we have this form. If they're double, then we times x. If it's higher, if we're triple, then x to the power of 2. Or if it's like there's imaginary roots, then we can write it like this. Not gonna go into it. Well, yeah. Guess it's okay. Well, yeah. Let's continue. Variation of parameter. What? I didn't know we did that already here, 7 point. Oh, not really. Well, it's completely empty anyways. What did I do here? Actually did quite a bit. Until 10. But yeah, we have this. We didn't even look at this, right? But if we have two solutions, y1 and y2, if we know them, and they're for the homogeneous equations, then we can find out the particular solution with this formula, or Wronskian, which is basically determinant of the matrix y1, y2, the derivative of y1 and y2. Yeah, and 1 would be like y1 would have the factor of y2 times this function over that. Matrix exponential, if we have derivative equals ax, then x is e to at, x0. Do we look at this? Yeah. Here we have like the formula. Do I have that? Yeah. If it's nilpotent, then we can use a series, and then it's finite, so we can just calculate e to the power of at with this formula. If it's diagonalizable, we can write it like this, and then the e's would only be on the diagonal, and then it's super easy to calculate. If it's a rotation matrix, then yeah, we get like the rotation matrix. Systems of higher order. And write x as this, and then we get the x prime to be this, and then we can solve it. And it shows the uniqueness of the solution as well. Oh, we didn't even look at separable ODEs, I think. Yeah, we didn't look at it, but something for next time. Basically, we just move this side to this side, and then we integrate both sides with respect to only one variable, so it's like easy. I'm gonna skip the exercises. Differential calculus in multi-dimensions. What does that mean? So partial derivatives, total differentiation, Jacobian chain rule, Taylor expansions. We'll look at this. So if there are several variables, derivative information lives in the gradients, so vector of partials in the Jacobian. Differentiality means a good linear approximation. So yeah, when we have partial derivatives, so x is not only, there's x1, x2, x3, x3, 4. It's the function of all this. So if xi is at the ith, only at the ith, we have the limit of h going to 0, while the other variables are fixed. Directional derivative is if we have some vector in some direction, and it is differentiable if in all directions it's, yeah, linear in this. Total differentiable there's a linear A, yeah, like this. And the derivative equals that A. So you have it's C1, it's differentiable. If it's differentiable, then the partials exist. Yeah. And it doesn't mean that it needs to be differentiable just because the partials exist. So it's C1, differentiable, partials exist. And then directional derivatives exist. That's the order. Oh, why? Why does it have to be so hard? I thought somehow I was like doing a lot better the last few days. The last 2 days I was like working a lot. So let's look at the Jacobian and the gradients. The Jacobian. So if we just have like one function, right? I forgot. No, if we have more, I think. The gradient is just one function and then differentiated to multiple variables. Jacobian is if we have multiple functions. So if we have like x and if our input is like x1, x2, x3, but the output is also like x and y, for example. So we have two functions and then derivatives. So we take the partials and they're continuous, then we know it's differentiable. Theorems, inverse function theorem, if f is c1 and the derivative of at 0, x0 is invertible, then locally f is c1 the diffeomorphism onto its range. So yeah, the derivative f Schwarz. Wait, actually, I'm not quite sure what this means. Schwarz is if it's C2, then you can interchange the partial derivatives. Something that's nice properties. Diffeomorphism. So we show that it's C1, and then we compute df and prove that the determinant is not equal to 0, so it's invertible. So local diffeomorphism. So here, what do we have? The matrix inverse, derivative of the inverse. Evaluated at that point. Also, G is the inverse. Is the matrix inverse of the derivative. We could show that it is bijective, so it's global diffeomorphism. Construct a vector field inverse. Proof C1. How do people focus after a heartbreak? I don't know. Implicit function theorem for x equals 0, xy equals 0, and if it's C1, if the determinant is not equals to 0 at that, then locally y equals h of x with f h of x equals 0 and derivative of h equals this. Example, fy is 2y not equal to 0, and for y not equal to 0, oh yeah, so it's for that not equal to 0, derivative y respect to x is minus xy. Would this be 2y inverse times 2x? So what is left is x minus divided by y. Some rules. Yeah, we've seen that already. Chain rule. It's part of my rise. So get an example. Squared y. Honestly, I'm not sure how I'm gonna do the next few lectures, if I'm also gonna record a video or not. Maybe I'll just study for myself. Taylor expansions in multi-dimensions. So yeah, then we would have the function itself at x0, y0, and then times derivative respect to x times delta x and delta y, and then 1/2 comes from the Taylor series, the K faculty, and then to the Jacobian of it, but yeah, written out. And this is only if it's C2, right? Then we can add it together. Oh yeah, here's the general formula. The Hessian, oh no, that was the Hessian. Yeah. Practical recipes, check differentiability at a tricky point. Usually it's the origin, continuity. See if the limit is independent of phi. Compute the partials. Show not differentiable. then there are different limits along different path. Why am I this tired? I'm trying my best. Chapter 9. Extremas. So yeah, we look at interior extrema occur where the gradient vanishes, if it's differentiable, and then we have to check whether the critical points are the min-max, or if that point is min-max or saddle, we have to look at the Hessian, and if there are constraints, we add the Lagrange multiplier. Good for optimization. But I can't remember. Oh my gosh. Whatever. So if it's unconstrained interior, then yeah, we just get the derivative and then the Hessian. If it's unconstrained on compact set, then we need to also look at the boundaries. If it's constrained, then we need a Lagrange multiplier. F minus lambda this. We'll look at it later. I also want to look at it again and remember it's just following a path. Kind of feels bad. I don't know why I feel that bad today. Let me take a pause. Okay, let's continue. So let's look at, it's where were we? Extremas. If we look at the second derivative, it's larger, it's a minimum, means it's growing. Like a maximum if it's smaller. And yeah, if it's zero inclusive. Well, yeah, there's like easy stuff here. Multivariable, unconstrained. So our critical point, have A is 0, do the Hessian. The Hessian test is the determinant of this. And yeah, if it's larger than 0, then we can say, check fxx, saddle or inconclusive. So we can see if this times this minus this times this, right? So if it's positive, then it means this times this is positive. So if fxx is positive, both are positive. If this is negative, then most negative. Total it's negative, so this has larger effects at saddle. Yeah. Yeah, basically we can also check the eigenvalues. Okay, so now find your parameterize boundary and optimize each piece. Yeah. Okay, now interesting constraint optimization. So we optimize f subject to some function. Then we can make the Lagrangian functions. Regular extremum. This one must be equal to 0. So sketch feasible sets, check compact and continuous, then extreme exists, then we can create the form. Then we solve for that. List the constraints, list all candidates. Let me do a better example. So yeah, but let's first start. This is our constraint, so x plus y equals 1. What? Guess. Ah yeah, this constraint, and we have the function xy. So we have xy minus lambda of this. Then can do derivative to respect to x and derivative respect to y. And then so x equals y equals lambda. And then the constraint here is 2 lambda equals 1. That means we have 1/2 for x and y. And why does this work? I think it was because if it's a maximum, even at that path, what was the reason? Derivative is also 0 or something. Right, so we can just add. I forgot. Maybe I'll also add that. And then I also want something else, 9.5. So we have something more complex. We have multiple constraints. So this function is for y minus 2x, 2z. The constraint of x squared plus y squared equals 1. And yeah, and this constraint. So I can build the Lagrangian minus Lagrangian of this, minus Lagrangian or lambda of that. And then 2x, we do derivative with respect to x, with respect to y, and z. Then yeah, we can figure out what the lambdas are. Let's build it. Yeah, I didn't finish it. Let's reload. Let's see. Did I change anything else? Yeah. Let's reload. See how it works. What goes wrong without Lagrangian? So an S point can be in an extremum without. S. S. Only tangent direction matters. So if it's lambda, so this be 0, the constraint. Oh, so we're finding the largest value basically along this curve. So it equals that, right? No. What else do we do? Oh, we just made this bigger. Yeah. So what is this here? Let's continue to integrations. We look at step functions, Riemann sums, connected to antiderivatives. Yeah, let's go into it. Step function is a piecewise constant on each subinterval. Only has a fixed number, so yeah, something like this. And an integral of a step function is just the length of that times the value. So on ST, it's that value between this. So here we see, yeah. I'm not gonna really look at it. The fundamental theory of calculus. This is the integral of this. It's like the area accumulated between a and x. F g is continuous. We evaluated, yeah. Well, I'll skip this. Riemann sums is if we like do tiny rectangles, take the limit, go to 0. Basically this, the step, we integrate the step function by having very small, what is it called, step length. It's like the derivative, right? And What am I doing wrong? Ah, yeah, let's continue. Swapping limits and integrals. If we decide if it's uniformly, then we can swap the limits and integral. Yeah, whatever, let's skip this. Improper integrals. So yeah, we can, like, if we have infinite integrals, we can split it. Deal with the limit. Or yeah, if we have singularity, we go towards that, right? Or we can split up the integral and then integrate. So yeah, let's actually look at an example. We need to decide convergence of 1 to infinity of this. For p not equals 1. We say to r as r goes to infinity, and then we can plug in the numbers. P minus 1, like we integrate, so 1 plus this, and then divided by that. Yeah. And then from 1 to r, so we plug that in as well. R minus 1. As this reaches infinity, we can check when it converges and diverges. The integral now. Inequalities, if g is smaller than g2, then the integral will also be smaller. If it's always positive, then it's a positive number, right? Easy. Yeah, I can say if it's positive and in a smaller domain, then it must be smaller than on the larger domain. What do we do here? We just compare the size. Yeah, we show that. Yeah, it's okay. I'm gonna skip it. Absolute value estimates. Absolute value is smaller or equal to, right, positive values of the integral. And yeah, if it's smaller than m, then you can write it as that. Yeah. Find integral. So if we integrate along a curve, not an interval, then the path has a density, or no, not necessarily a density, but if we walk along a curve, we need to scale it. We'll see it here. So if we walk along f, along this gamma, then we can reparameterize gamma with AB, but then we have to have the integral have the derivative of gamma. Yeah, and for work, it's similar. That's multi-dimension, right? So yeah. Let's look at an example. We use a path lambda t equals t and t squared. Then the derivative of that is this. Yeah, in scalar case, we say the function is just x. Then f of this, if we place it, then it's t. So it's t times this, and then yeah, we can integrate. Not gonna look at it because I did it already too much. And yeah, if it's work, then we do it like that. T squared plus 2t squared is 3t squared. Ta-da! Conservative vector fields. Then we can use just b minus a of the vector field. What was it? If it's conservative, then phi of x equals this and phi of y equals this. I think it needs to be continuous. Where the things that needs to be, yeah, whatever. So any path leads to the same solution. That's why we can use this. Oh yeah, this has to be proved. So yeah, dp, so the x, the first of dy and second of dx needs to be same. Then it's conservative. And no hole. Okay. Oh gosh, my motivation is so fucking low. Okay, I shouldn't swear. But yeah. Oops, I cannot cut it out. And I'm too tired to cut it out. It's okay, I shouldn't swear. Do I want to do an example? Yeah, let's do it. So it's 2x to y. We derive, where do we test here? It's a conservative. So here we have p 2x to y. Yeah, and then from the other one, it's both 0. It's the same. Then we find phi by integrating, and then integrating, or knowing that the derivative of this needs to be that h of y, and then we can integrate it, so it's just x squared plus y squared. Well, yeah, and then we can just use the potential formula. Integration rules. So we have different ways of integrating. We can integrate by parts. So it's the reverse product rule. So yeah, if we have u dv, we can say u times v minus v du. When was it used again? If we have like, oh here. When do we, I thought if we have e to the power of something and then x times that. Well, yeah, I'll figure it out. Integrating. So yeah, we have polynomial, we can lower the degree. ln x, yeah. Let's go for an example. X ln 1 plus x. Then u is this. dv is x dx. du is 1 over 1 plus x. And with v, so if that is dv, here we integrated x squared. So we know it's like, so basically calculating the integrating, something like the integrating factor. Or no, I mean just its integral. It'll be this times this minus the integral while deriving the other side, which would be, right, 1 over 1 plus x. This here times this, yeah. And then this is probably easier to solve. So you know this is easier to integrate. Gives this, we integrate, yeah, so yeah. Substitution rule. So if it looks like some derivative times the inside times the function outside, then we can use the chain rule in reverse. And we substitute, find du, and when we replace, we'll have to divide by u, right? Because du is this, so divide by this, so we remove this part, and then it's easier to integrate. But be careful to also change the boundaries to match that. Okay, so when do we use this? So if it's like power compositions like this. So let's look at this. You see here, this looks like the derivative of this. So use 1 plus this, d use this, divide by, get the 2x out. Right, so it's 1 over u is 2. This is easy to integrate, if we change variables, then we can see what happens, right? We need to, 1 over a. I mean, this is pretty much from here. So I'm not gonna get into it too much. We change the boundaries, and this is the derivative that came out. This is another example. I'm not gonna do it. Frequent integrals. So we have this or this. Substitution. Polynomial times e to the power of something. Sine, cosine. We integrate by parts. Sine and cosine, we would get the same term, and then we can solve it easy. Parts by twice. Oh, this is what I meant. So we can integrate it twice, and we can solve for the integral. Because we should get back the same thing again. or something similar. Rational functions, we first divide, and then partial fractions. If we have this, trigonometric substitution, yeah. So let's look at some integrals. If we have x to the power of p gets to +1 and divided by this, easy. ln of x, it's 1 over x, e to the power of x stays, cosine integrates to sine, sine integrates to minus cosine. Yeah, ln of x is x times ln of x minus x. Yeah, let's do an example. This ln x squared minus ln x, absolute value of x minus x. Yeah, and as it's positive, it's okay. Yeah. And then some more special functions. 1 plus x squared is arctan, arcsine, arctan h, arctan hyperbolicals, or whatever it's called in English. Hyperbole, I don't know. Do we have, yeah, this just needs to be learned by heart. It hurt. Where do we have? Do we have any? Whatever. So we have power times exponentials, then we do integration by parts multiple times. Yeah, until it vanishes. Let's look at this example. Parts, the first one, it gets smaller, right? And then we only have e to the power of x left, and it's easy to integrate like this. Or easier. I mean, this would be what we want to integrate, right? We just integrate e to the power of x. So we get this, not like integrating this. What am I saying? Yeah, if it's like this, we do parts twice. And then we can like, this looks similar to the first one. Wait, what? If we do it again, I think. So it looks like this, right? We get a plus minus I, and then two i's, a plus b. Oh, here we see the I again. Bam. Receiving closed form solutions. Yeah. Pow pow. Do. Yeah, we have powers trigonometric. We can use the identities. Well, I have to learn that by heart. Yeah, let's go through an example. We can twice. Yeah, well, I guess it did some shortcuts, but yeah, it will be easier to integrate this. So over 2 pi, if it's different, then it's equals 0. If it's not the same, same with cosine and sine. Yeah. Rational integrals. Let's see this. We do polynomial division. Or no, we don't need it because it's smaller up here, and then we split 2x numerator. Oh, and then denominator 2x plus 1. Wait, what? Like this is what we get, right? Yeah. It's equal to this. And we can use the arctan. So you're right. Split it. Oh, that's a different way than solving what I thought. I'm tired. Hard time. To make it easier to integrate, t plus squared. Oh, I think I need another break. Taking so many breaks. Yeah, my body's feeling weak today. Even though I did sports. Maybe because I didn't eat enough. Whatever. gonna look too much into this. What's that sound? Okay, I'm gonna skip this. Maybe some other time. Solids of revolution. So if we have a function, then we have r times this, then we can like write into volume of sums, yeah. So if we have like slices all around here, we integrate, get the volume. So PR, p times radius squared. And the other way around, if it's the y value, so it's like x times this. How do I feel? Oh yeah, it should be okay. Yeah, I'm a bit tired to go through all this somehow. It's a bit boring. Integration, multi-dimensions. Yeah, we can make a box. We can have a function of the size of the boxes, and then one, so integrate it along one area. We can exchange the integrals. I think here was it Fubini. The order of the integral does not matter. It's the continuous. Well, just want to skim through everything. What is it? 3. Let me check. And then what do we see? Let's continue. Oh, let's skip this. I'm too tired for this. Integrate over normal regions. Well, yeah, somehow motivation is so low. Yeah, but yeah, I mean, here you see how to integrate it. And we walk through. We have x between two values, and it has to be, the y has to be between this, I guess, limited by this upper bound and lower bound. And we have this. Type 2, y is the outer, like flipped. Well, should I have not skipped this? I don't know why. I'm sorry, guys. Oh yeah, and here we integrate on the other side instead. So x squared is lower, and then y1 is the upper bound. We integrate up until here, and x is 1. Yeah, just how the bounds are defined. Yeah, it's like the constraints, right? We check the bounds and then from that we think of a way to integrate this. So if we see this, x and then y, so we know that we integrate, so y has to go from x squared to 1, while x is 0 to 1. Yeah. Okay, we change variables, distorts the area or volume by a factor, so we need to multiply by the determinant when we integrate the new domain. I thought I had a graph it somewhere. No way, I don't have it. Yeah, here I have it. Also, we will see it later on. Oh, that graph is quite nice, so let's do this. I mean, let's skip this. But useful to know polar coordinates, how to map, and well, it doesn't say cylindrical, spherical. Yeah. This is what we already did. So here we see the determinants. If we switch it to a polar coordinates, we need 2 times r. So dA, dB would look like this. Same for cylindrical. And spherical is r squared. And sine this. Yeah, let's look at polar coordinates. Phi is an angle from a thing, and r is the distance away. So if we move here, right, we would see it moves by r. If r is closer, right, we do smaller circles. But in phi, it's same. So we change phi linearly, but here it does a small move, whereas if we have a large one, if we do a small step, we have like larger move. That's why in polar coordinates we need 2 times r to get that effect. So yeah, we can think of a small rectangle maps to a curved path here. So a small rectangle, a small move. So we move along the curve, which is scaled by r. Can think of if we move along, then we move like r. Well, it doesn't go to 0, and then we move again. Now patch. I think this is nicer here, you can see it. What, isn't this the way to go? Whatever. So here we see if we have, you know, if it's we increase R, actually we have to increase dr, so we see the volume scales differently. So here if we move R, we're always the same volume, same area I mean, but here when it's a small R, it's a small volume, but if it's a large R, it's a larger volume. Yeah, especially if we do this, it's easier to spot. Here, just an explanation. Annulus. Or would have been easy to show that we go through here and then we skip and then go on the edge if we go like this. So that also needs to be scaled. Let's say between R equals squared. If cylindrical, it's similar. Let's see, scaled by R. And the sphere, we can also see. Now in the sphere, we need to have the ratio of this. Right. Factor R squared sine of this, because if we have let's go for a large R, dr, let's go for dr, it's easy to spot. And this, it's like how wide, this doesn't matter, or not as much, because if we move up, you know, like this one, if we move left and right, it doesn't change, like the area does not change. But if we move up and down, let's go for up, we see we have a different area, so that's why we need 2 times the sine. And of course the distance, the R matters. And here we just see like it always stays the same, it just like translates in the x, y, z space. So we do this. Want some more example? I'll skip it. Green's theorem and Poincaré. I feel like I'm not sure if I should study today. I'm not learning much. Or maybe I should switch something. Or because I've already done it, so it's like twice as boring, 3 times as boring. I'm sorry if anyone is watching till here. Like, I don't expect anyone watching. Yeah. So, I mean, this is like transforming area integrals to line integrals, etc. So here, what is this? Why only the boundary appears the tiling? We chop this into many small rectangulars, and each cell green holds miniature. The line integrals around the cells cancel out on the inside. If we go this, right, this cancels out. It's 1 time plus, 1 times minus. So only the outer boundary is left. That's why the integral over the whole area can just be a line integral along the boundary. And yeah, it doesn't matter here. So yeah, Green's theorem. It's bounded. You have a path around the boundary. So we walk along. If this is like a swirl, I think, then we can just do the line integral. What do we do here? So we have a vector field with components p and y. If it is so yeah, we have the curl. It's the same, yeah, it's what we saw. Well, somehow I want to learn when I actually need it. Oh, I'm so sorry, guys. I'm not feeling good. Yeah, I'm not gonna do examples. Be like swirl. All right. So V is conservative, so like a vector field, potential field, I mean. So this, they're equal, then closed loop is 0. Yeah, that's That's what the theorem is. Surface integral, so if we have what is it called, a ball, and then we have flux, how much passes through the curved surface is then the flux integral. So how much is generated inside. Well, I'm gonna skip as well. Let's continue. Volume integrals, we have a density mass, then yeah. Now it's equal 1. Well, it's easy. Center of mass. So yeah, it's average position weighted by density, and then yeah. Almost Gauss. Oh, this is what I meant. Total creation inside is the net outflow through the surface integral. Guess that's Gauss. So yeah, if we have a volume and it's a divergence, can just calculate the work along the surface. Skip this potential fields. Yeah, I want to skip it as well. Or actually, let's go through it. Potential field is a vector field that is a gradient. So integrals reduced to endpoint differences. So if V is this, then the work along any path depends only on the endpoints. What is there to worry about me? Let's just go through examples. Find the vector field by integrating P. We have given this, the vector field, test if it's conservative. We see both the same, so they're conservative. We integrate it. We find the potential field. And then we can use potential to, oh, what? Why is this here? Whatever. Yeah, no holds. Well, yeah. Vector analysis. What is it? Gradient, divergence, rotations, Green-Stokes, Gauss. When to use it. Oh, I guess it's like a summary of before. The divergence is what's, yeah, gradient, rotation is, the curl is, yeah. Topology, open sets. Oh, I want to skip this as well. If it's open, there are no boundary points. If it's compact, it's closed and bounded. Jordan measurable. Boundary 0 or no weight, and it's bounded. Yeah. Should have, whatever. I feel like if anyone is watching, they're just watching me suffering. Yeah, I want to skip this. Some useful formulas, I guess everyone knows that. Some additional things to see. Well, yeah. Yeah, I want to do some other things and not do this anymore. Complex numbers, maybe I'll do one summary on that, because I had a complex analysis. Okay, whatever. Yeah, if anyone watched till here, thank you guys. Yeah, for watching. I feel like my other videos are better. But yeah,